Thank you for joining the session. In these 30 minutes, I will try to show you a different way for optimizing test case suites. Before we begin with the agenda and so forth, I want to mention that usually during talks, when I'm on conferences, for me it's more valuable to get inspired about the different projects. It's not always about the code and the library, but about the different approaches, the methods. And I think this will be the most valuable thing for you. I will touch briefly on what metaheuristics are, because I'm sure that it's not very popular. This is like a totally different branch of software algorithms that are different than the regular ones. But also, I will show you two demos that you can get inspired to try something like that in your particular context. So first, I will start with defining the problem, compare it to how we solve it with traditional approaches and their limitations, like pairwise testing, boundary value analysis, and so forth. And then we'll proceed talking about how metaheuristics can help us, what they are, in short, because even the introduction to this field is like at least 4 hours lecture. So I will try to explain it with simple words. And then I don't want to bore you with lots of theory. So there will be 2 demos, one of the library and then another one of how we can use it with MCP servers in AI agents in such automation workflows. And also, since this is like, as I will mention in a minute, I'm not selling you a tool or anything. It's open source project, and actually it's a result of my, let's say, scientific work or curiosity, whatever. And actually, I'm actually very happy because yesterday it was approved and it will be published in a couple of weeks as a scientific article in one popular Switzerland scientific magazine. So yeah, it's a scientific work with a lot of experiments and math behind it. So let's begin. So first, what is the core testing challenge? To give you an example, I will use self-driving cars. Imagine that when you have one self-driving car, how do you test such a system, AI system? It's very hard because there are like astronomical number of test cases. Imagine that you have the different types of roads, like highway, mountain road, city road. Then you have different weather conditions, like sunny, foggy, it can rain, it can snow. You have different road conditions, like pedestrians or different cars from the left, from the right, signs might be missing. You have at least 20 sensors that have various configurations, and maybe at each particular moment, one of them can break and something might happen. Just for 10 parameters with 5 values each, if you do full combinatorial testing, you end up with more than 10 million possible test cases. And some of you here are QAs, you know that one of the, even maybe the first testing principles is that exhaustive testing is not possible. We cannot do full combinational testing. And with the case with the self-driving car, you can imagine there are billions of test cases. It's not possible. We need a smarter way. And recently, in the last few years, I'm reading a lot of papers, scientific papers about testing of AI and QA, etc. And such problems usually are solved with one traditional approach. It's combinatorial approach. It's called pairwise testing or all pairs testing. This is a combinatorial approach for those of you who are developers that actually minimizes significantly the number of test cases while it preserves only test cases where at least in one test case each pair of inputs is present. And in order to explain that, imagine a simpler example. You have this web form. In this web form, there are some fields that we don't care about them, like the color picker, etc. But let's imagine that we have 5, 6 of them with 3 possible values. Like, we'll discuss in a minute the ranges, but for example, you can put 3 names, we can limit to 3 names, 3 emails, 3 phone numbers. You end up with all combinations around 5,000, 15,000 combinations. If you use pairwise, depending on which tool you use and technology, you end up between 50, maybe 100 test cases. And the approach that I will show you with metaheuristics, we can further optimize the set, maybe in half, but you will receive like maybe between 20 and 70% better test case quality. In a minute, I will explain what this test quality means. Why traditional methods are not working very well? In pairwise, because it's combinatorial approach, you are just combining all of the values, you don't care whether they're at the edges of a particular range or not. Because if we are here, imagine that for the full name, in the database you have a constraint, like the name can be between 10 symbols and 100. For the age, it can be between 1 and 120. And for the QAs, you know that we have boundary value analysis, meaning that we are testing at the edges of the ranges. Why this is important? Because for the developers, you know that when we are writing code, we write with conditions, right? If conditions, whatever, and many often we use greater than, equal than, and if we miss the requirement, if we miss the equal sign, there will be a bug. There will be a bug exactly at some of the edges of the range. This is why this technique exists. We usually, when we have a range between 1 and 120, we take the valid boundary, which means 1 and 120, then 0 and 121, etc. Equivalence partitioning is much simpler. We usually group the input parameters, for example, valid, invalid, security parameters, whatever. And this heuristic says that when we use one of the input parameters from one group, then we don't need to test the rest. However, this in practice doesn't work very well because there are interdependencies between the parameters, and this is usually why we combine it with boundary value analysis. And as I said, pairwise testing is just combinatorial approach. It doesn't care about ranges, it doesn't care about equivalence partitioning, and also there is one more heuristic usually that it's used by QAs. And this heuristic is that especially when we write unit tests, automated tests, we don't combine multiple invalid parameters in a single test, because this will cause the so-called bug masking. Meaning that, for example, here, if you want to check all of the validations rules, and if you put, I don't know, wrong full name, email, phone, etc., you won't know if you test with all invalid values, whether you're not bug masking another problem. This is why the heuristic is that we test only with one invalid value. And this is why, actually, now it's the time to explain how these meta-heuristics work, and then I will tell you how I combined all of those together to optimize further the pairwise testing. So meta-heuristics are very interesting. They're different than standard algorithms. The standard algorithms, for example, sorting, etc., they can be proved with math. They find, most of the time, if you use the right algorithm, the most optimal solution. Meta-heuristics, on the other hand, they cannot be proved very easy with math. They're nature-inspired. What this means? You heard terms like evolutionary algorithms by Darwin evolution. You have genetic algorithms. There are some algorithms that are inspired by animals, like the base algorithm that I used is actually called artificial bee colony. It's inspired by how the bees are working together, because there are 3 types of bees. We have, for example, algorithms about ants and other animals. But again, I promise not to bore you with theory. I'm sure that actually on a daily basis, you're using a lot of apps that are behind the scenes are using meta-heuristic algorithms. If you're using Google Maps, behind the scenes, when you click find the optimal route to go somewhere, it's not using a regular algorithm, calculating all of the optimal routes. It's using some kind of a meta-heuristic to find the near optimal very quickly. This is the base difference. It's doing it very quickly, but it's not finding the most optimal solution. It's finding near optimal, which most of the cases is just fine for us. And this usually happens because under the hood, these algorithms, they're using a random element. And this is why it's very hard sometimes to prove it with math. I will give you another analogy. When you go to the Vitushka Street and you want to find, if you go straight and you want to find a very good restaurant, you can go just straight, like normal algorithm. However, if your meta-heuristic algorithm, sometimes there will be a random element that will cause you to go left or right. And sometimes you'll find a very great bar that it's somewhere in the small streets. This is exactly how these mini search algorithms are working in meta-heuristics. Another apps that probably you are using are, for example, YouTube, Spotify, Netflix. These algorithms that they suggest you, sometimes they're using AI, but before AI, they were using meta-heuristics, right? And another example, if you're working in or if you went to a university, and I'm sure that all of you have the schedule. To make a schedule for university, this is extremely hard problem. Because imagine you have thousands of students, 20 buildings, thousands of rooms with different equipment, with hundreds of professors with all different requirements. No professor can be double booked, no student can be double booked, and the next hour that you need to take, it needs to be in a building that it's nearby. Imagine how hard it is to build a program like that, and usually this is done via meta-heuristic algorithms. And now it's time to show you really quick, a short demo. Here on the page, you can see the Testimize, at least a short version of the snippet of the library. It's doing three things. It generates the test data, it's generating the test cases, I mean, using pairwise and optimizing it further, and after that is generating the tests themselves. Like here, we're using this Testimize generated test case attribute, and when you build the project, it will generate from the right, you can see the generated test cases automatically with all of the data and everything behind the scenes. How we do that? First, we have the Fluent interface, where this is why I said that it's very extensible, which means that for each input, imagine again the web form, you have a text field, email, phone. Here we are mentioning the ranges, like the valid range where we can put it. So behind the scenes, it will generate the boundary values. But also, if we go to this configuration, we have the so-called equivalence classes, meaning that it will generate very interesting cases for emails, for phones, with a particular precision. And we have that for many different fields. However, there is a slight problem. As I told you, meta-heuristic algorithms, they are not deterministic, which means that because of this random element, we are finding near optimal solution. However, just a second, because I'm not showing you the code, actually. Sorry about that. Yeah, so we have this configuration here, JSON configuration, where we have these interesting values, right? These are the equivalence classes that we can use. And yeah, and as I said, we are using these ranges here to generate the mode. However, as I said, it's not deterministic, which means that every time there will be a slight change in the test cases generated. This is not very good for continuous integration, right? Because every time you have a little bit different test cases. However, this is the so-called, I call this mode, exploratory mode. It's similar to exploratory testing, because very often when you develop, for example, web API, GraphQL, unit tests, whatever, you want quickly to run something like that, very quickly the library to generate the data, the test cases, to run it, to find some bugs, and then you can use the so-called precise mode, where this is very precise. I mean, here I listed all of the different possible inputs that I can place, whether they are valid, whether they are boundary valid, what is the expected message, etc. This is like an ultimate test. We can leverage again the library itself to generate everything. As you can see, there are many fine-tunings. But in the end, it will copy to the clipboard, and to the console output, it will generate all of these attributes for you in any format. I mean, there are various formatters. For example, we can generate JSON, we can generate NUnit, MS-Test, XML, whatever format you want. And again, once generated, it will stay the same always. And now, how actually this works under the hood. Maybe the next demo will be a little bit more interesting for you. This works in the meta-heuristics. Many often they rely on these fitness functions, evaluations functions, that basically give a score about one of the items. In my case, this evaluation function is calculating the quality score of a test case. What this means, for example, if you have a test case with 5 input values, we need somehow to measure whether a test case is a good or bad. How we do that? We combine in this function the different inputs. For example, if you have an input for email, we are categorizing it whether it's a boundary value, whether it's boundary valid, meaning at the edge of the valid range, or outside of it. And we are giving a bonus of it. For example, if it's just exactly 1, which is a boundary valid, we give like a score of 20, which is very high. However, if it's inside the range, this means this is not interesting value, right? So we are giving it a much smaller bonus. And also, if you take it, if you look at the beginning of the function, if you have more than 1 invalid values, we are giving a big penalty, -50, which means that if you have 2 invalid values, most probably this test case will be dropped. It won't be used later. And yeah, if we have, if you see at the bottom, if you have more than, if you have a value that it's new to all of the test cases, we will give a bigger bonus. Again, I understand that it's even this is the simplest part of the algorithm anyway. It's really hard to speak about topics like that. Anyway, when you start with the algorithm, you see here the UML diagram, a simplified version of it. Usually, this artificial big colony starts with completely random generation of the inputs of the test cases. However, this is not very optimal, especially for cases with millions of test cases, right? This is why under the hood, one of the things I changed, this is why it's called a hybrid approach, because it's combining, I don't know, maybe 6 or 7 different meta-heuristic algorithms. So under the hood, one of the changes is that we use pairwise generator, the NUnit pairwise generator, and we are optimizing from there. After that, we have multiple iterations through the algorithm, for example, 100. Each generation, we are calculating this score about each test case, and we take just half of it. I mean, we take, it's called elite population, which means elite test cases, the best scores, the test cases with the best scores. And then, for the next half, we are mutating them. Probably you heard the term mutation testing. Maybe you can relate to that. The thing that we do here is that we are mutating the input values, meaning we are on random, we are changing some of them with other values, and we are recalculating the score. And this is the important part about meta-heuristic algorithms. They are working with trial and error, but we need a way how we can measure whether the next thing is better than the rest. This is why this function here is at the core of the algorithm. It's the core logic, how it works. Now, let's stop with the algorithm itself. Here, you will see another important part. These are the different parameters that you saw, that you can fine-tune how it works. Even if you used on a low-level LLMs, you know that they have various parameters that you can use and fine-tune based on the different contexts, how they work. And this is very important about meta-heuristic algorithms. They rely heavily on various different ratios. For example, here we have a mutation rate, which we can change. depending on what is the value, whether we change 30% of the test cases or 40, it can significantly change the final output. And another important part, I think I mentioned it during the slide about metaheuristics, is that we are not proving that with math. Actually, we use statistics and variances, etc. However, we do that with extensive experimentations. For example, in order here to find the optimal ranges, I did at least 1,000 experiments with different settings. You can imagine that. And we use like math to prove that it's not happening on random. Again, this is like a requirement to be a scientific work. Anyway. So here is the table, a simplified version, because here is with the math. But here you can see some of the parameters and why it's better. As you can see, the improvement with 67%, we need to compare it, like, as you know, in testing, in performance testing, etc., we need to have a baseline and something, an hour thing to measure against it. In my case, I was comparing against the pure pairwise, just like we are taking half of the test cases, again, sorted by this evaluation function, compared to if we use the hybrid artificial beam algorithm. And in many cases, actually, it's better, like here you can see the math, 15 different configurations. Like in half of them, the improvement is over 15 to 20%, in some cases, like over 60. And one of the key things that I want you to remember, that in metaheuristics, we need to use high math statistic variances to prove that some observation is not happening by luck. For example, this P number at the end, where you see 0.001, this means that all of those experiments prove that this is, there is 0.1% chance this to happen by luck. It's not happening by luck. And usually over 0.5 is good, below that. And now I want to show you maybe the more interesting thing for you will be to see a demo. Actually, I incorporated this library in an MCP server, and I combine it in a just a minute. So the demo that you will see, I'm basically using in Visual Studio Code a couple of MCP servers. The first one will read some requirements from Confluence about the different ranges, right? Then here I configured in my Visual Studio Code with MCP servers Jira, Zephyr, which is a test case management system. Here I built in C# the MCP server for Testimize. And also I use Playwright to automate the test cases at the end. Through experiments I found that actually AI is not very good in generating boundary values or pairwise. It's like for 10 cases, maybe it will do it, but if you have more, it totally doesn't work, or you cannot prove that actually generated pairwise. This is why we need MCPs or outside tools or libraries to do that. So yeah, in this demo, I will load the requirements or reading the requirements from Confluence through the AI. I will instruct it to read it from Confluence. Then it will use Testimize to generate 100 test cases, optimized version of them with the test data behind the scenes, directly in the AI. As you can see here, we can get the settings of the algorithm and we can change them, we can fine-tune them. By default, here I listed with this particular tool the default values, but we can change them in plain text. As you can see here, I changed the mutation percentage, how much of the test cases we can mutate. And now I have an assistant from the left that I'm showing right now with different steps. I used prompt engineering and prompt patterns to teach it how to read the requirements, what is the template for the test cases, that later in a particular step I want to create the test cases in Zephyr, then that we are going to start the browser, we are going to execute the test case in the browser, it will find the bugs, and then it will create the automated tests with Playwright and generate not Playwright code, but Selenium in Java. And as you can see here, we are reading at the bottom the Confluence page, and now first Confluence search get page, then we're calling generate hybrid test cases with the Testimize MCP server. As you can see here, I visualized some of them, again with all of the data. Now it's starting with Playwright MCP, the browser, executing all of the scenarios in the browser, and it generated the Selenium code. It's not Playwright. We are using Playwright MCP, but we generated Selenium Java code, not TypeScript. And after that, as you can see, when we close the browser, it closes the tab, it will generate test cases for our approval. When we approve them, it will, in step 4 here, it will create them in Zephyr. And like if you download, there isn't official Zephyr MCP. I forked one and improved it a little bit to include steps and expected results. But yeah, in a second you will see that we open Zephyr and we will see that actually all of the data, all of the test cases we generated with the Testimize were created in Zephyr, in Jira, with all of the data. Again, usually this is extremely hard if you rely just on AI. This is why MCP servers like that are very important. As you can see, the data that we generated with Faker under the hood using Testimize. And even in the end, here I'm using another MCP server for loading Slack, and in Slack I will post all of the IDs for the test cases that we generated. This is full-blown scenario with this assistant. And you can combine it, you can imagine what can happen if you, for example, use tools like Cursor or Cloud Code, right? This is just Visual Studio Code, which is like not the smartest of them all. Yeah, just a second. All right. Something happened. All right, so I have a little bit of time, but a couple of things that I want you to remember. First, metaheuristics, that they're very important. Again, you can use these algorithms to solve very complex problems, especially if time is essential for you. As I said, they're used in apps where time is essential and you don't have the computing power to do it. Like on your phone, you cannot calculate all of the routes, right? And you need to remember that we are finding near optimal solution, not like sometimes we need the best solution, then you will use standard algorithms, but when near optimal is fine, then you can use them. Also, remember, when you use AI, LLM, chats, etc., they are very bad when they generate data, boundary values, or pairwise. For sure, you need to double check that they're doing the right job, but in most cases, they don't. And this is why we need outside tools. Like, you can use this MCP server or another, but you need to remember that you need an outside tool for that. Also, one key thing in metaheuristics is that don't trust assumptions. For example, here I did many different experiments to find, for example, the different weights. If you remember the function here, and you're going to ask me, actually one of the professors that proofreaded this paper asked me, how you prove that this should be 20 and not 50, which is an accurate question. And actually to prove that, I did like 7,200 experiments with different configurations, with 5 different schemes of how you calculate that. And in reality, I was thinking initially, okay, maybe when you change these numbers, they will really change the final output, right? It's obvious. However, it's not obvious, because all of those experiments proved that when you change these values, actually it doesn't change much the final output. It's not common sense. This is why we do experiments. Actually, the only thing that matters here is for this boundary value, if, where you see it, when we give the bonus, to be much higher than the one for the valid values. That's the only thing that actually matters. Actually, it turns out that the whole structure, how we group, how we give bonuses or weights, is more important than the actual values there, which is not common sense. And you need to find that through lots of experiments and, again, using math to statistically validate that. And yeah, you can check the GitHub repo. Even if you don't use it, it's very interesting to see how different design patterns are applied. For example, Fluent Builder and others like Strategy, etc. It will be just, you can be inspired just to see how this architecture works so that you can extend it further. Thank you.
Okay, do we have any questions? We have time for 1 or 2 questions.
Hey, Tony. What made you choose the artificial bee colony and not something like the artificial ant colony or another genetic algorithm?
To be honest, I read some papers that this particular algorithm is very good in generating tests. Initially, I read such a paper, and I had to pick one of them to develop something. And this is why I said, okay, maybe I will just experiment and see how it goes. I want to implement something myself. And this is how I did it. Actually, after that, when I was doing the scientific research, I read many other papers, and it turned out that most of the people were actually using this particular one. Because most of the algorithms, they are very good in particular area, right? And that's
Thanks.
Anyone else?
Yeah, we can talk
Okay,
later
yeah,
in the
thank
breaks
you.
if you want.